So our next speaker is our own Fayyaz Minhas. Fayyaz is an associate professor in the Tissue Image Analytics Center at the Computer Science Department, University of Warwick. And Fayyaz obtained his PhD with Fulbright Scholarship at Colorado State University and has been with us for almost 4 years now. And Fayyaz is now very much interested in designing machine learning models for integrating digital pathology and bioinformatics data. And today he's going to tell us about causality and domain generalization. So over to you, Fayyaz.
Just a couple of logistical questions before I begin. Do I need to stand here or can I move around?
Move around as long as people can hear you online.
Yeah, that's what I'm not so sure about. Do I need to carry a microphone?
So you can carry one of these if you prefer.
Yeah. And do we still have 30 minutes?
Yes.
Yeah.
Okay.
So I think this would be okay here.
I mean,
I managed not to reach.
because load as possible, at least people can also hear you.
When you're moving around, just make sure just ask people online if they can hear you.
You want to start?
Hello. I think everyone can hear me in the room, but can people online hear me?
You have to.
Yeah, it works.
Okay, thank you. So we'll be talking about causality and domain generalization. First of all, yeah, thank you. If I don't mess it up. So this is there, right? Okay, perfect. Thank you. So thank you to the organizers. It's been a pleasure organizing and thinking about actually this talk. I've learned so much and during the workshop as well. So really thank you to you. Based on my teaching experience, this is absolutely the worst time anyone can ever give a talk. If you're sleepy, just listen to one of the questions and then what would causality give you? And after that, you can go back to your state. So let's ask the question. Yeah, why did the neural network get seasick? Any ideas? Well, I asked this question to ChatGPT, and this is the answer. Because it wasn't trained for the high tides of domain shift. It kept making predictions based on land data, and when it encountered the vast ocean of new data, it just couldn't stay afloat. And we know that that is a real problem. That's what we've been talking about all day, right? Domain generalization, and how, more importantly, it's important to understand why that happens. Because all of the methods that we deal essentially try to solve the problems that we encounter during related to the problem. So we know that machine learning methods, once you develop them in a certain scenario, they will work if you train them well, if they're given examples that are very similar to the training examples. However, as soon as one of the things changes, if you got a different scanner, if you're using different stains, if you have a different pathologist and a different, so who labels their slides differently, if you have different types of input, your method has been trained on H&E, even if it's the same cell, but now the staining is IHC, your method will not work, or if there are population differences. So those are very computational pathology specific examples of why this is a problem. And we've listened to many talks that are giving us very different approaches and very interesting ones on how we can solve that. What I'm going to do in this talk is hopefully convince you that all of those approaches that we've talked about, these non-causal approaches, as I call them, they have some fundamental flaws, as no amount of data can fix that. So that's one part. After that, you can go to sleep after the second part. And then what do causal domain generalization methods do differently? And what do they offer? They primarily offer two things. One of them is they help overcome some of the flaws that are available or present in these non-causal domain generalization methods. And the second bit is they give you a different way of thinking, which I think is more important than actually solving the domain generalization problem, because we can go beyond domain generalization. So we know that domain generalization at its core, the reason it happens is that there is a difference in the train distribution and the test distribution, or the source distribution as it is called in domain generalization lingo, and the test distribution, which is called the target distribution. If this IID assumption is this identically distributed assumption that forms a core of different machine learning methods, if that goes out of the window, then we have problems that require solutions through domain generalization methods. So we have 4 different types of domain shift, and probably Mustafa is going to talk about in more detail of this. So I'll just very briefly give you some examples of each type of domain shift before moving on. The first one is covariate shift. So what happens there is that your distribution of the data, if you, let's say, are making a machine learning method to classify cancer versus non-cancer, and you use data from one scanner for training and the other one from testing, then the source distribution of the images, the PX, is not the same as PX target. And hence, if you just use the Bayes rule, then you would end up that the joint distributions of the source and the target will no longer be the same. So that's one thing. Prior shift is another type of domain shift in which your ratio of positive to negatives or the labels changes between the training and the test. So let's say if you use site A for training and site B for testing, if they have different proportions of positives and negatives, then you would need to probably adjust some of the thresholds of your prediction method to retain the same level of accuracy. Posterior concept shift happens in computational pathology quite a lot as well. Let's say you've got 2 different pathologists. They are given exactly the same slide, but because they have different concepts of what is a certain disease in their minds, then that leads to disagreement between them. So here, the labeling process of generating the label from the given image is different between 2 different things or 2 different pathologists. So if you use data from one of the pathologists as training and give the other data from the other pathologists as test, then you would end up having problems. The last type of domain shift is what we call a class conditional shift. In this case, let's say you've got 2 sites, you've got negative and positive images. The negative images across the 2 sites look roughly the same, but the positive images look different. And that can be one type of class conditional shift. Only examples of one type of class are changing. Now, typically, it doesn't really matter. Once we get a domain shift, it can be one of these 4 types, and characterizing it would give you some insights into why that is happening. But we actually get a mix of all of these types of domain shift in our data. So most of the time, the discussion we've had is about covariate shift, but there can be other types of shift present, depending upon what problem you're trying to solve. So how do we handle it? We've listened to a number of talks. So I'm just going to very briefly talk about some of the methods. The first method is, of course, not to let domain shift happen. So you control your domain shift by standardizing. Let's say, if you can force everyone to use the same scanner, the same dye vendor and everything, then probably some of those variables would go out, but that is always not practical. So we can do that in silico. That's the next best thing. And one way we can do that is to use stain normalization methods. Those have been traditionally used for this purpose, but our work, and I'm going to talk about towards the end of this talk as well, has shown that and by others as well, has shown that it may make the images look the same way, but it doesn't take out any subvisual cues that can still be exploited to link the source site to a given image, and hence it's not a solution for domain generalization. Another way you can do that is we've talked about augmentation quite a lot. The previous speaker did an excellent job of doing it at the test time as well. So here the main idea is that we make the machine learning method, we give it images, not only the true images, but also perturbed versions of those. And then we hope for the best. The next bit is we take things into a bit more control, where we want to make the neural network train adversarially over these perturbations. So we make the neural network try to fail the neural network by introducing these perturbations while trying to retain a good level of accuracy. So we have a toolbox that allows you to do this for computational pathology. We call it robustness enhancement and evaluation toolbox. And what you can do is you can do different types of computational pathology specific augmentations using the toolbox and see whether that improves your generalization performance or not. Another method that can be used is self-supervised learning. Here, the goal is that you can use large quantities of unlabeled data to hopefully learn representations that are invariant. I'm keeping the word hopefully and maybe and those, and I'll come to that why I say that in just a minute. Ensemble learning is another way. Instead of training one method, you train multiple methods, and hopefully the combination of those is going to perform better for domain generalization in comparison to any one of those. The last two categories are regularization. So if you got a method, machine learning method, you may want to regularize it. So a method, it is like a theoretical proof that if you don't use regularization, then what you end up with is a method that is very sensitive to small changes in the input. So regularization methods can help with that and hopefully generalize to unseen test cases better. Domain alignment is another method in which we use a loss function like KL divergence or Wasserstein loss, and we want to make the two distributions of the training and the test data, we try to align them. So that is the goal of this. We can also use meta learning, and I'll let Mustafa come and explain that during his talk, hopefully. But all of these methods are there. Again, this is a very quick whirlwind tour of all of the methods. There are so many others that I've missed. But those are the broad categories of these methods. And what you can do is you can put all of them in a box, shake it, and sample from that distribution, and you get another method for domain generalization that hopefully works again for your problem. But all of these methods implicitly try to model the effects of domain shift, not explicitly. And that is one of the fundamental problems with most of these approaches. So my criticism of these approaches is this. Non-causal domain generalization methods implicitly minimize the worst case error, and they're associative in nature. As a matter of fact, most of the machine learning that we use is associative in nature. And what does that mean? It means it's essentially based on the following concept. You've got two images, you know label for one of them, but if the other image is very similar to this one, then probably this image also has the same label. As long as that association holds, so we are going to do okay. But once that is out of the window, we get problems. And these domain generalization methods, they don't explicitly model what is the data generation process and how things are causally linked to one another. And I'm going to talk about that in just a minute after this slide. So if we look at some equations, of course, it's a machine learning talk, right? So let's say we've got a set of positive and negative examples, and we want to train a machine learning method by minimizing a risk function like this. So what we want to do is to minimize the loss or the expected value of the loss over the joint distribution from which the test distribute data also comes. So if the test data comes from the same distribution as the training one, then this classifier is expected to perform well on the test data. But going back to the definition of domain generalization methods or domain shift, the test distribution may be very different from the training distribution. So all of these methods that I've just talked about, these non-causal domain generalization methods, they try to solve a variant of the empirical risk minimization. And it's conceptually quite similar. Don't look at the equations, they scare you, but let's look at the picture. So we've got these data that are given to us. We perturb in one way or another. We can use augmentations, we can use adversarial training, we can use regularization with the goal of smoothing out these boundaries. But what we are trying to do is we are trying to optimize not only the explicit or the exact distribution that is given to us, but also in the neighborhood of that distribution. So coming back to the equation now, we are trying to minimize the loss function over a set of distributions that are sampled in the neighborhood of the training distribution that is given to us. So most of these non-causal domain generalization methods, they try to solve this type of domain of machine learning problem, where we're trying to minimize the worst case errors over all possible neighborhoods of the given distribution that is available to us in training. And once that is there, you get this classifier, and most of the time it works very well as well. So it's not that I'm overly critical of these approaches that they don't work. They have a flaw that I'm going to talk about, but this is what they do, and sometimes it works. But it's mostly you try to sample in the neighborhood of the given distribution and then keep your fingers crossed that hopefully that is enough to make the problem go away. So why causality for domain generalization? What can causality to do that other machine learning methods cannot? So I took this picture out of the book of Why by Judah Pearl, and he talks about that currently all of these machine learning methods that we have are at this rung one, or they're very associative in nature, and they're very probabilistic. And that is a problem because they don't model the causal structure of the data generation process. I'm going to quote some of the stuff from the book and from some of the papers in this literature to inspire you why we need causality for this particular case. So the first quote is from Judah Pearl. It says, a machine trained in one environment cannot be expected to perform well when environmental conditions change unless its changes are localized and identified. So if you don't identify what is causing that change, cause is the key word here, you cannot expect the model to learn very well. The second is, if you want to make a machine that does this, that is able to generalize across domain, then what you need to do is it requires a causal model of the environment, and we cannot be properly addressed at the level of association. So if you got just an associative model without any causal information given to the model itself, we cannot expect it to perform very well. So let's say if you just use association, then a machine trained on one set of images in which mitosis are darker in comparison to neighboring cells will not be able to perform well on images in which mitoses are not darker in comparison to neighboring cells. So that is the key. And another way of, like, if you want to make this machine, then what you want is you need additional information or mechanisms of learning the underlying cause or invariant structure of the problem. Most of the non-causal approaches try to learn the invariant structure of the problem implicitly, whereas causal domain generalization methods go a bit beyond and they model the causalities in the data generation process more explicitly. So if you so far understood nothing, this is a key statement. So domain generalization approaches, all of them, causal or non-causal, can be thought of as ways of incorporating causal structures or invariances into predictive models, either implicitly in the case of non-causal methods or explicitly in the case of these causal methods that I'm just going to talk about. So to understand this, I'm not going to go into the detail of what causality is and what is a cause and an effect. If you want that, I've actually recorded a longer version of this lecture, sort of, on YouTube, and you can go and watch that. But for this discussion, what is important to understand is what do we mean by causal and non-causal features. So this is an example. So if you look at this figure in which we've got a car on a bridge, and we ask these counterfactual questions, then if we can answer these counterfactual questions, then we can understand which are causal features and what are non-causal features. So let's ask the first question. What would the scene look like if we were to remove the car? If we remove the car, the bridge would still be there, the water would still be there, the sky would still be there, I would still be there, and so on, right? It wouldn't change anything, except if our task was to predict whether there's a car in the image or not, right? Because that would change the label. Then if you ask the question number two, what would the scene look like if we were to remove the bridge? If we remove the bridge, where would the car go? Would the car still be there? Until Tesla invents floating cars, that's not going to happen. So that is a critical cue. We can ask these counterfactual questions, and there are statistical methods that allow us to ask these questions to infer what object is causing what other object, or what objects in a given image are associated with the label. So in this case, the bridge is our cause for the car to be there, because if you take away the bridge, the car also goes away, right? And most of the time we represent these causes in these causal diagrams in which we can say that the bridge is a cause for this car to be there. Similarly, we can also say that if we are trying to determine whether a certain object in a given image is a cause for its label, let's think of another counterfactual question. If our goal is to detect cars in this image, and then we put a black area over the car, right, over here, and we ask the question, is the car still there? No. Or is this image still contain a car? No. By masking certain things, we can discover whether there is association between a given object and its label, and that allows us to infer what objects in a given image are causes of the label and causes of other objects in the given image. I'll not be going into the detail, as I said, that would take quite a long time, but I hope I've given you the concept of what a causal feature is. It's essentially a feature that is associated with the target that you want to predict and nothing else. The sky, in this case, doesn't matter. The background doesn't matter if our goal is to detect whether there's a car in this image, right? So what causality gives you is a very different way of thinking about your machine learning problems. If you think like you take the classical view, then you have a real world phenomena and you are sampling data from that joint distribution. And we know that your input features X are associated with the label Y. And that is pretty much it. The causal way of thinking is actually more detailed. We think about the data generation process, and instead of going into this generic example, I'm going to talk about a more classic causal view of the data generation process in computational pathology. So let's say we've got a real world phenomena. Someone gets a disease. They have a disease in them, and we don't know what the disease is. They go to their doctor, and the doctor takes a biopsy, and the biopsy is scanned, and we get an image. So the disease mechanism is unobserved. We can't see inside a person, right? So that's why we take a biopsy out. So this is unobserved. But that disease mechanism, let's say cancer, causes changes in their histology. Those changes are captured in an image. But there are other factors that also affect the image. For example, the slide preparation process. The digitization process also affects, and there can be other factors that affect this image, right? This image now is given to a pathologist, which assigns it a label whether the person has cancer or not, right? So this is the observed truth, and typically pathologists are really robust. They look at only causal features. If some of the background changes, they're not thrown off by that. So the pathologist label is based on some of the causal features of the image, and that is why we ask pathologists to label our data for us. This label is also dependent upon the experience of the pathologist, right? So two pathologists may have very different notions of what a certain disease is, and that's why their labels can be different. This label assigned by the pathologist determines the person's treatment, which in turn determines the patient's survival, together with patient's age and other demographic factors. Now, this is the view that causality gives you of the data generation process, instead of just thinking about it as, okay, we've got two variables, one of them is X and the other one is Y, and both of them are correlated, and that is the associated view. This is the causal view. This is a very simple diagram. I'll try to simplify it to the extent possible. Now, there is another factor over here, as you can see, site, that affects slide preparation. Different sites may have different types of dyes, different vendors of the dye, and that may affect how the slides are prepared. Similarly, they can have different scanners, so that will affect that. Site also affects the distribution of people that enter that site. So you get data from, let's say, South America, it's going to look very different from the data from Europe, right? So your site is also affected over here. This causal view of thinking about computational pathology tells us some interesting things. One of them, look at the importance of site. If you know the site of an image, that tells you implicitly that there would be what type of slide preparation there would be, what type of digitization there would be. And even pathologists experience, some sites are specialized to work in breast, whereas others are more focused towards, let's say, colorectal cancer. So the experience of pathologists can also be indirectly linked to that. So site is really important. Knowing site is useful. Yeah, I'm just gonna, okay. Yeah, so that's why if you've taken nothing away from this, that is one of the primary difference between non-causal approaches and causal approaches. Here we take a look, or a deep look at the data generation process and look at the importance of site. That means that's why we actually want multi-site validation for all our computational pathology methods, because it is causally linked to so many other factors. Okay, moving on. So causal domain generalization methods, I've got 5 minutes to cover all of them, so I'll try my best. The fundamental idea is, if you remember our non-causal domain generalization methods, there, what we were trying to do is we were trying to minimize loss, or the worst case loss, in the neighborhood of the distribution. Here, what we are trying to do is we try to think of domains, so data from different hospitals think, as explicit interventions or changes over non-causal features. If someone has got a cancer, and assume that all of our pathologists are really good, if they walk into, let's say, the University Hospital of Coventry in Warwickshire, or they go to Nottingham, their cancer is still going to be diagnosed, right? Hopefully. And that is because the pathologists are not going to be thrown off by these non-causal variations. So if you show a pathologist an image from a different site, they're still going to be able to do it. So the interventions that come in, the effects of domain changes are non-causal. That's the fundamental key insight into why these methods would work. And then the way we use causal domain generalization is that we try to simulate those type of interventions and try to minimize the worst case error over those interventions instead of doing it implicitly with the hope that it would work. So if you were to do causal domain generalization, the first thing that you would do is construct a causal graph like the one that I talked about, identify what your sources of variations are, and then try to explicitly model the effect of each one of them in your machine learning process. And hopefully, again, no guarantees here as well. There are certain scenarios in which this would fail as well. But these domain shifts, so what we've learned so far is that domain shifts can only change features that are not causal. We can identify causal features through interventions of statistical asymmetries, and we can then learn to disregard those features. If a machine learning method does that, then that would qualify as a causal domain generalization method. Okay, and there are three broad categories of those. One of them is, of course, causal data augmentation. The second is causal representation learning, and the third is causal invariance mechanisms. Given the shortage of time, I'm just going to briefly talk about the fundamental idea behind each one of them, just very briefly. So the fundamental idea of causal data augmentations is you synthetically generate counterfactual examples by perturbing only non-causal features, and you perturb the hell out of them. Like there is no tomorrow. So if we know that staining is not associated with the label, then that is a non-causal feature linked to the label. And then you can perturb it as much as you like. It is going to improve your domain generalization. And that's what we've seen in the talk earlier as well. So causality gives you a framework of understanding why certain methods work as well. It also tells you why this would fail. If you perturb something that is that is causally linked to your output, you're going to screw your machine learning method. So if you perturb a feature that is causally linked, that's going to be really bad. Another limitation of data augmentation methods, these ones or otherwise, is that they only work when, so let's say, if the structure of the task between the training and the test is the same. So if you want to use a machine learning method that you trained on H&E, but you give it an IHC image, no amount of augmentation that you can do would work in that regard. So that is the key. There are some causal domain generalization methods out there. I'll link those in the slides and you can take a look. The second category of methods is causal representation learning. Again, here the goal is that we want to be invariant to causal factors that are different across domains. So we want to build a representation and then pass it to a simple classifier such that that representation doesn't capture anything related to the domain. So a simple method that does that is this gradient reversal method, in which what we want to do is give it an image and then try to predict the label of the image, but not the domain of the image or where the image came from. These methods are called class conditional invariance methods, and they will fail in these scenarios. So if you've got two domains, let's say domain 1 and domain 2, you've got these two positive and negative classes. And then what these methods would do, all of these categories, what they would do is they would learn to disregard feature X2 over here, and then learn to classify on the basis of feature X1. But if your test distribution is different, these methods would fail. They would give you lower accuracies. So these methods, the interpretation is marginal domain invariance methods or class conditional invariance methods are not sufficient for generalizing to unseen domains, and they will work only if class conditional distribution of the features remains the same across the two domains. Otherwise, you're looking at failures. Causality, there are some methods like causal matching that allow us to solve that problem. I'll just skip the slide and move on to the next one, which is the third category of methods. So the third is causal invariance mechanism, and the way these methods work is you want to again learn the representation so that a very simple classifier on top of that would give you very interesting or useful labels. Again, this talk has already been recorded, so you can take your time understanding this. So I'll end over here. how to solve a practical problem when in domain generalization. You start and you try to set a baseline, and if that works, you go ahead and enjoy. You don't need to worry about anything else, right? Otherwise, if it doesn't work, then you can go ahead and check the amount of domain shift that you have. The way you can do that is through simple, let's say, sorry, I just need to go back a little bit. You can just do UMAP plots or PCAs of the training and test data, and those look different. You will end up with domain shift, right? But it is difficult to quantify those. So what you can do is try to predict your domain from the given images. And if that happens, there is definitely domain shift present. And if it is significant, then you can identify some of those sources of variations and try to limit their effect. And if that effect can be limited, you are back to being happy again, right? But if that doesn't work, then what you can do is try simple augmentations of causal features, or sorry, non-causal features. And if that works, you can go ahead and enjoy. You can do it with regularization. You can also try to get domain data for the test domain. If you're especially building medical imaging or a medical machine learning problem, because in the end, it is the accuracy for the patient that matters, okay? Other than that, you can do adversarial training, and if nothing works, you can go ahead and use causal machine learning methods. And that's pretty much it. If that doesn't work, you can give a presentation like this, or you can start reading Albert Camus and think everything is absurd and not care about it and move on. Okay, so that's pretty much it. Thank you so much. Again, the link to I think it's on my last slide. If I could just show that. Yeah.